This is part 2 of the Gibbs free energy. Let's dive into the learning check. Consider the composition of yellow mercury 2 oxide. So mercury 2 oxide forming into liquid mercury, and you see this rather uncomfortable value, half of oxygen gas. Calculate the standard free energy change at room temperature 298 K. Delta G naught, case looking for delta G naught, using the Gibbs free energy equation and the standard free energy formation equation. Do the results indicate the reaction should be spontaneous or non-spontaneous under these conditions? So let's target A first. The Gibbs free energy equation, if you recall, A is delta G naught is equal to the delta H naught minus T delta S. The only information that we have so far is T, which is the temperature, the 298 Kelvin. So we could plug that in. But we don't know delta H, nor do we know delta S. And that's what we're going to try to figure out, the delta H and the delta S, enthalpy and the entropy change, in order for us to solve for delta G. So let's target the enthalpy first. So delta H. Delta H equation would be it's very similar to the free energy formation equation, and that was for Gibbs free energy. Now this is for the enthalpy. So that will be the summation of the H product, and my product are mercury liquid and oxygen, half of the oxygen. So I'm going to go ahead and write 1 mole, since there's 1 in front of the coefficient of the mercury, of the enthalpy for mercury, plus, since it's a summation, 1/2 of the enthalpy of the O2. So I have this in here. There we go. And then subtract it with the reactant side, which is summation of the 1 mole of the H naught, and then this is for mercury 2 oxide. Okay, so we have these guys in place. Now we need to find the values of these, and that will be in your reference sheet. So go to your reference sheet and find those values. Because to hunt for those values is going to take quite some time. So I recommend like a table on the side in order for you to find out what those values are. For example, you're going to need something for mercury, you're going to need something for oxygen, and for mercury 2 oxide, right? So you'll need the value for delta H naught and also entropy right at this point. You will eventually need to find for delta G naught as well, but for now, what you're going to do is you're going to go to that reference sheet and find these values here and plug them in here so we can work with that. And I'm going to go ahead and do that right now and then come back. So I went ahead and found all of those for you, and hopefully you were able to find those as well. So let's go ahead and plug this in. So here, this is equal to 1 mole of mercury, which is 0 actually. So that's 0 kilojoules per mole, plus 1/2 of the oxygen, and that would be 0 as well, kilojoules per mole. And this all in summation, and you subtract it with 1 mole of mercury 2 oxide, and that one is not 0, but rather negative 90.46 kilojoules per mole. Okay. Now everything on this side over here, it's going to be just 0. So we're only dependent on here. So this is -1, right? So this be negative, and here's another negative that becomes positive. So this value, delta H, will be just 90.46 kilojoules. And the moles are gone because these all cancel out. Okay, so that's for delta H. Now I want you to go ahead and find for delta S. It's the same deal. You do the product minus the reactant, the summation of it, and then put them together and calculate that and come back and check if you have the right delta S. So hopefully you were able to get 107.2 joules per Kelvin. Please note that there is a Kelvin sign and this is a joules. If you look on the left, the enthalpy is in kilojoules. So you must change this into kilojoules, or you must change the other one into joules. Either or will work, but I'm going to go ahead and put this in kilojoules. So if I were to put this in kilojoules, 1 kilojoule is equal to 1,000, or 10 to the third joules. So joules could cancel out in units, and I get 1072 kilojoules per Kelvin. Now I have my delta H, I have my delta S. I do have a temperature, so I can go ahead and plug into this equation where you have, I'm going to go ahead and do it in a different color to kind of distinguish. Leave a little room on the bottom. We can put that into G naught is equal to delta H naught minus T delta S naught. And what is my delta H? My delta H is my 90.46 kilojoules. My temperature is the 298 coming from here. So 298 Kelvin. And my delta S is 0.1072 kilojoules per Kelvin. So Kelvin can cancel out, and we can solve this out in our calculator. So I have my 90.46 minus the 298 times the 0.072. Hit enter, then I get 58.51 kilojoules. So 58.51 kilojoules. And what does that say about the spontaneity? So since it's a positive value, this is non-spontaneous. Okay. Now I want you to take this. I'm going to erase some portion of this area since it's pretty dense right here. And I'll leave the green portion and the table on the side as is, but then I'm going to erase everything else so we can start comparing the part B with A. So let's go ahead and erase all of these and then go with part B. Okay, so I went ahead and erased everything, and I found all the delta G that I needed in order to plug into the Gibbs free energy formation equation. So I'm going to go ahead and plug all of these in right now. So this is equal to 1 mole, and G mercury is 0 kilojoules per mole. And then we have the half of the oxygen G naught, which is also 0 kilojoules per mole. And this gets subtracted to, I need that summation, to negative 50. Ooh, I apologize. I need to write 1 mole. 1 mole and negative 58.43 kilojoules per mole. Okay. So I should get just 58.43 kilojoules per mole. So the one on the bottom was part B, and this was one on the bottom was part A, and the top one is part B. This is part B now. Now look at the comparison between the delta G. So this one for part B for formation was 58.43, and this one from part A was 58.51. So they're fairly close, and that kind of indicates that you probably did the calculation correctly. If one is like 10 and the other one is like negative 100, there's something wrong. There should be congruency, some similarity. And on top of this shows that this is non-spontaneous. Few joules off, like 1 or 2 joules off, that's totally fine. Points are definitely okay. So you can see how when you come across these kind of equation, yes, you'll need to know how to utilize both equation, but the easiest way would be to utilize the standard free energy of formation equation, because you don't have to look for delta H's, you don't have to look for delta S, because that gives another level of challenges.